Alright, so looking at the time, I think I may not have enough time today in the synchronous lecture to go over the lab because I also have other stuff that I need to go over. So, the solution is to go over the lab in a recording. So that's what we're going to do. So this is the lab from last time. It's a simple branching and code analysis. So what I'll do is I'm going to I will go through the lab, as if I'm, answering those questions. All right, question number one: the increment instruction increments the value of a register, but it does not affect the flags. This makes the instruction more useful because in many situations the objective is to add 1 to a counter address, but it is also important to preserve the flags from a previous compare instruction. Use the opcode table or the assembler. Find out the binary opcode of the following instruction. Alright, so let's go ahead and go to the opcode table. I'm not even sure whether that tab is still up here or not. So I'm gonna look for it. There we go. Oh, it's not even in the same browser. Well, that is interesting. So I'm gonna move this one up here and resize the window. And I will do some other stuff later on to get this to look right. There we go. Alright, so we're looking for increment, and since it's in column B, we just highlight column B, Control F, and then just type increment, and there we go. Alright, so increment is right here. The bit pattern is 1101 and then XXXX. So each XX is referring to the register. So this one just kind of repeats it. Alright, so I think we're ready to answer that question, which is in a different browser window. So now I need to move tabs around and just kind of get everything to consolidate a little bit. Alright, so we'll move this one right here. And I also have my notes. And I'm going to move it right here. There we go. Alright, so now we can answer this question. Oh, I forgot about the binary bit pattern already. It's 1101, which is a D in hexadecimal, and we want register A. So register is easy because that's just zero. Oh no, this is increment C. So register C is 10 as a bit pattern. So when we repeat it, when we have two occurrences of it, it becomes 1010, which is an A. So the correct answer is D A. Oh, it needs to be a binary number. I cannot read my own instructions. Alright, so there we go. 1101, which is the fixed bit pattern, and then 1010 is the part that specifies register C. Alright, moving on. Alright, the Jmpi instruction has an immediate operand. When it executes, it changes the program counter to whatever the immediate operand specifies. Consider the following instruction: Jmpi to some label. When this instruction executes, the processor continues to, alright, bad grammar here, the processor continues to execute where some label is defined. This unconditional jump/branch instruction is useful to handle the case when a conditional branch jump does not branch. This is mostly because TTP lacks conditional branch instructions that branch when the flag is cleared, when it is 0. Consider the following code. Compare AB JCI L1 JMPI L2. If execution continues at label L2 right after the code, and assuming L1 and L2 are defined at different addresses, what can we conclude about registers A and B? Alright, so this question, we did not talk about JCI in class, but there was some discussion of CMP, which is compare, which is basically just a subtraction. So what we can do now is to look at the opcode table and see how JCI is described. So instead of looking for INC or increment, now we look for JCI, which is right here. So the description of JCI is the program counter is getting whatever the program counter points to when if and only if C is true. Otherwise, it goes to PC plus 1, so it just kind of moves on. And if you read the English description, it means it says jump if and only if the carry flag is set. Alright, so that's one piece of the puzzle. The other piece of the puzzle has to do with CMP or compare. So now we need to take a look at compare and see what it's doing. So CMP is right here, and CMP is kind of um, cryptic because all it says is x minus y. That's it. It doesn't even store the difference anywhere. So so we're gonna take a look at that, and this time we're gonna take a look at this in the emulator. So let me see. Do I have the emulator up? Nope, because I had to restart my computer last time. So that's okay. We can just go ahead and find a text window or CLI and restart that. So we're gonna go to LogicSim. I have a script to start LogicSim quickly, so it doesn't take up too much time. All right. So now we go to Open Recent, and we want to open processor 0004. So either one is going to work. This one's going to work, and then so is the other one down there, but I'm going to use this one. There we go. All right. So the question is, what is being stored in the flags register, right? And that depends on the ALU. So we look into the ALU, and now we see, oh, okay, there's a whole bunch of circuitry here. What are we gonna do with this, right? So there are a few things you can do. The first one is to understand what CMP actually does, and you can do that by looking into the opcode of CMP AB, find out what the pathways, how the pathways are done between the components, and you will find that A goes into this wire, and then B goes into this wire when we have CMP AB. And then we have this kind of mysterious component here. We have no idea what it is, so let's click on it and find out what it is using the selection tool. And it is a subtractor. All right, so a subtractor, if you look it up, in the references, so you go to help, go to library reference, and then you go to arithmetic library, and you go to subtractor, and you'll find the subtractor doesn't do a whole lot of exciting stuff. All it does is to subtract. Okay, so in its own documentation, it subtracts it subtracts the subtrahend from the minuend, and obviously you kind of have to know what those terms means, and that's pretty easy. You can just look it up using Google. So in other words, all it does is to do a compare, is to do a subtraction. That's what compare does. But what is interesting is, what about the carry flag, right? So when you look at the output pin, flags out, which connects to the D port of the flags register, there's a C out, which corresponds to the carry flag. And when you look at that one, cannot modify circuit, obviously we cannot, because it's a subcomponent. So when you look at C out, now we switch back to the poking tool because we want to find out where it is connected to. So when we click on this wire, it highlights to be this one, which comes from a multiplexer. And then the multiplexer is going to feed different things into C out depending on the selection pin, which is the one that has a gray dot on top. So that is the one that specifies the operation. In other words, depending on what operation we're trying to do, it will route different things into the C flag. So now the question is, what does CMP, what does compare, how does compare as an instruction route things? So now we can look into the compare instruction. Oops, I just did something that, oh, I lost the opcode table. Okay, so I'm not sure what I just did, but I just lost that tab. That's okay. Let's see. Let me go back to. Do I have that tab? Nope. All right. So I just need to find the right tab to get back to. There we go. Shared. All right. So now we can go back to processor and then look at opcode table. And then we look into CMP. CMP AB to be specific. Now the opcode of CMP AB, you can figure it out just by looking at this, which is 1110. That's a C. And then we have XXYY. So in this case, because register X is register A, so XX is 00, and then YY is register B, which is 01. So together we have 1110 0001, and that would be a E1. Okay, in hexadecimal, that's a E1. All right, so now that we know it's a E1, you can poke the instruction into here and just wait until you are done with the fetch cycle and then the decode cycle, and then you can get to that location in ROM that specifies all the pathways. Or once you understand that the microcode pointer is really the same as the instruction, which is the opcode, left shifted 4 times, then we can just kind of key in that code. In this case, it is E10. Alright, so now the ROM is already at the location of E10, which means the pathways should be configured properly now. So we can double check. Okay, so we can double check and make sure that the ALU is indeed enabled. You can see the light green wire, it is enabled. It should be routing register A to in1 and routing register B to in2. So once you get into this situation where you can't really tell whether it's routing it correctly or not, when we are trying to understand the processor, we can actually go in here and just kind of poke some values into the registers that we're dealing with. So the easiest way is to say register A has the content of AA in hexadecimal, and the register B has the content of BB in hexadecimal. I mean, that should be pretty easy to remember, right? Which one is which one. So now when we poke in 1, we see AA, and we poke in 2, we see BB. But what we also want to know is what operation is being specified, and that's the cell line here, which connects to ALU operation, and it's specifying operation 001, which is a binary number. So now we go into the ALU and find out what that means. Alright, so we can see the demultiplexers here, which basically routes in 1 to one of the operations and route in 2 to one of the operations. And we can see opcell operation selector is 001, which means the input of a demultiplexer is connected to output 1 of the demultiplexer. So that's how we can connect in1 as an input pin to the minuend port of the subtractor, and this is also why we are connecting in2 to the subtrahend of the subtractor. Now the subtractor does have a borrow in, but the borrow in is always connected to 0, which means that translates to our T0 when we talked about binary subtraction. So in this case, it's always a 0. Now there are ways to kind of hack this, so that it's not quote unquote always 0, but we are going to talk about that later. What is more interesting to us is the borrow out is a 1. Okay, and we can see how it connects to a tunnel called B. So now we need to track down this B, which is down here somewhere, right here. Okay, so this is B. You can see how B is going into this multiplexer, and this multiplexer shares the same select as the overall operation. So that's 001, and because this is a multiplexer, it means we are connecting input 1, which is B, to the output. So after all of this discussion, that means if B, the borrow out, which is the same as our T8 in our own terminology when we talked about binary subtraction, so T8 is basically C out. Okay, so borrow and carry are basically the same bit when we store that into the flags register. All right, so this is a gigantic detour, right? Because now we can get back to the question that we were attempting to answer. Okay, so right here. All right, so we basically end up with A minus B. A is what we usually call X, and B is what we usually call Y in a binary subtraction. And we end up with, and then the C flag is the borrow bit, the overall borrow, which is T8 in this case. So the question is, what does it mean when we end up at location L2? So according to the description up here, and also according to the description in opcode table, we end up at label L1 if and only if the carry flag, or in this case the borrow flag, is set. So that means we end up at label L2 if the borrow flag, if and only if the borrow flag is not set. So that's the only thing we know. We know that in the subtraction of A minus B, T8 or the overall borrow flag is cleared. That's all we can that's all we can say. So if you go back to the binary subtraction module, um, the meaning of the overall borrow being a 1 is when the minuend is less than the subtrahend in an unsigned interpretation. So we can basically rule out all the signed interpretation stuff. So all the ints we can rule out. So we only got two choices left, which is unsigned greater than or equal to, or unsigned less than. And I just mentioned it's not less than, right? Because if it is less than, then we have the borrow flag being a 1. So the correct answer is greater than or equal to. But the important part is how we can track down everything using the processor. Um, so that's kind of the important point here. One of the more useful tools in Logisim is to debug and gain insight of a program is the ability to log and trace components. This feature is accessed in the simulate menu, blah 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 blah. Alrighty. So when after the processor is loaded into Logisim in the selection tab of the log window, what is the fifth entry of the left column from the bottom? Oh, this one I am not sure that I have it fixed already, but we'll see. So we go to, let's go back to main first. And then we go to simulate, and then we go to logging. And it's asking for the fifth item from the bottom. Alright, so I hope I got this fixed already because I changed the layout of the processor, and every time I do that, it changes the positioning of these components. So that should be RIENCLK, or Register Input Enable Clock. Alright, so let's go ahead and put that in. I don't think I have fixed it, but we'll see. Register Input Enable Clock. Alright, next. If I haven't fixed it, I'll just give you the points, manually. So question number 4 is it's kind of the fun question because it requires you to put in your student ID in a backward order down here. And then the program needs to have JXI replaced by one of the 5 conditional branch instructions. And I just want you to count the number of times the no op at L2, not L1, but L2 executes. So this is L2 right here. So in this case, L2, you get to L2 if and only if the JXI instruction did not happen. So if there's a table for you to fill in, to basically tell me how many times JCI, JZI, JSI, JOI, and JLI execute. So you can do this by empirically, which means you're just going to run the program and then count and trace it, or you can also theoretically just kind of figure it out. No, so now I can use my ID as an example. So my ID is 0006887, but it's going to be backwards because the rightmost one is going to be the first one. So it's going to be 7 8. I don't understand why the spacing is off. So it's 7 8 8 6 0 0 0. All right. So this is not how I expect you to get this done, but this is how I got it done. I can't get it done. So basically what the program is doing is comparing adjacent digits. So it's comparing 7 to 8, 7 being the minuend and 8 being the subtrahend. So in this case, for the first one, so I'm just going to use a notation here. It doesn't like that. Okay, so Shift Enter works better because it's not exactly a hard break. Alright, so in this case, there will be a carry because 7 is less than 8 in an unsigned fashion. JZI would not be counted because they are not equal. JSI would be the same as C, and then JOI is always going to be a 0, and then JLI is always the same as a C. So L is going to be set, sign is going to be set in this case. Then we move on to the 8 compared to the 8. It's not going to be a carry, it's not going to have a sign, it's not going to be less than, but it is equal, so Z is going to have an entry here. And then the 8, 6, none would have any entry because 8 is not less than 6, does not equal to 6, so none of the flags is actually going to count in that case. 6 versus 0, once again, nothing. The first 0 versus the second 0 is equal, so Z is going to pick up one more time, and then the second to the last 0 versus the last 0 is also equal, so Z would count again. So in my case, oh, I just made a mistake because I counted backwards. So these are the cases where the flags are actually set, but since we count when the flag is not set, so that means C is going to be 5 JCIs, 5 JSI, 5 JLI, and the Z would be because it's 6 minus however number we counted up here. So in this case, it's going to be 6 minus 3. So Z is going to happen like 3 times, JZI. And then JOI is kind of the funny one because JOI never happens. There's no overflow. Because a single digit is only going from 0 to 9, which is not enough to cause an overflow, because 0 minus 9 is negative 9, which can be represented by an 8-bit signed integer. So if you cannot remember how we can determine the range, you need to go back to talk to the module that talks about signed representation. So basically, JOI never happens, and since we're also counting, the occurrences of JOI happening or the other one, we're counting the occurrences of JOI not happening. So it's going to be 6 times. So in my case, it's going to look like this: 5 JCIs. In the case of JCI, 5 times. Okay, it gets to the no instruction 5 times, and so on. All right. I'm just looking at the time. It's not quite the time to teach the class yet. Okay, I got some messages, in my text channel, but that I can wait just a little bit. So what I want to do is I'm actually going to copy and paste this code into a text file, so this way I can actually run it. So let me put it into. I'm doing this off the screen so you can't see it, but it's boring CLI stuff that I'm doing right now, so no need to worry too much about it. Alright, so now we can edit the file. And change the JXI to JCI, because JCI, JLI, and JSI, they all have the same counts. Okay, so I just change it to JCI. Alright, so this part I do want to show because it is kind of cool, because I'm using my own River Spider tool. So let's see. So I can run my River Spider tool. I cannot remember whether I can do it from elsewhere. Apparently not. I did not put a shortcut into my bin folder. So I'm just gonna have to change my folder to Documents, CISP310, River Spider. and then the program itself is in my temp folder, but that's okay because submit actually can work with the file in any folder. So I can now just direct it to temp slash ttp asm and then run the code. There we go. Alright, so now everything is done. I go back to the assembler and then we go to the analysis tab, and I need to find out what is the address at location L2, which I can find out in the assemble window. So L2 is here. It is at location 17 in hexadecimal. So I just need to count the number of times 17 appears over here. There are a few ways to do it. The quickest and easiest way is just do a Control F, which activates the search, and we're just looking for 17, and right away it says 1 of 6. That is not what I am expecting, because I'm expecting it only to... Oh, right. I forgot to change my ID. Alright, so this is my little mistake here, because I forgot to change the array to my own ID spelled backwards. Okay, so 7, 8, 8, 6, and then 0, 0, 0. So let me just double check. 0, 0, 0, 6, 6, 8, 8, 7. Okay, that's right. Okay, so let's do it one more time. Now this is really kind of magical because you can actually get to see the submit script in River Spider, and also you get to see how Google Sheet changes. Like it should change automatically, not instantly. It does take a little bit of time, but we'll see. All right, so there we go. Yeah, so it updates right away. 1 of 5, so it occurred 5 times, and it just reflects the result like right away. Well, I cannot complain about that, right? So there we go. So what I said earlier is correct. JCI, JSI, and then JLI, they all occur 5 times, and then JZI occurs 3 times because 6 minus 3 is 3, so it occurs 3 times. JOI occurs 6 times because JOI itself never happens, which means we always, when we change XI to JOI, we always end up at label L2 because JOI to label L1 never happens. But you don't have to figure it out, just by understanding what the instructions are actually doing. Because what you can do is to you can just go ahead and run the code and find out. Because the whole exercise is trying to get you to understand how to trace your code. Because being able to trace your code is going to come in really handy for the rest of this semester. All right. So let me check the time. Yeah, I still got a few minutes before the class has to start. So a few things, okay. River Spider is handy, but it's not the only way to do it. So the other way to do it is to run Logisim on the command line interface, collect a trace file, and then upload the trace file to the assembler. So that's the other way to do it. It's a little bit laborious, okay, but it's doable because I have been doing it for years until I finally got tired of having to do everything manually, and then wrote the scripts in River Spider. So that's just a convenience feature. It's not necessary. But being able to trace your code is actually quite important. So even if you don't use River Spider, knowing how to use Logisim to collect the trace, which is in the form of a TSV or a tab separated file, and then importing that into I cannot remember the name, trace raw data, that's important. And that reminds me, I think I mislabeled that in my documentation, so I should probably fix that and then re-upload the README file. So yes, Omer, already pointed out that in the README file, or in the script, it says the trace analysis sheet, but it really is just analysis here. I simplified the name because otherwise it takes up too much space horizontally. Then I forgot to update the documentation. Very typical of programmers. You change the code and then you forget to update the documentation. So the next person who has to take over your project is going to go scratch his or her head and go like, I don't know what's going on here. All right, so I'm gonna fix that and then really get ready for the class. And so this portion is kind of pre-recorded just so that in class today we can focus on what we really need to talk about today, which is the structure of a conditional branch. Even though this program does touch on it a little bit, this new project, the new lab tonight, is going to need that too. Alrighty, so I'm gonna shut down the recording, upload it, and I get ready for class.